to this Okay, good. We can
Okay.
start.
Hello, everybody. Welcome to our seminar this afternoon. I'd like to introduce Scott Gaudi from the Ohio State University. He was very particular about that. It's been a pleasure to work with Scott for some time. He did his PhD in exoplanet detection by microlensing at the Ohio State. And he has specialized in exoplanet discovery and characterization ever since, microlensing especially, but also transits. And he's had a huge impact on the whole field, for which he has received many, many awards. And he returned to Ohio State later on as faculty. He has been working over the last year down in Caltech on a sabbatical, so we're very lucky that he has come up to come and see us today. Scott is PI of the Roman Galactic Exoplanet Survey Project Investigation Team, of which Katarzyna and I are collaborators. So we're very excited today to have him come and tell you about all of the awesome science that the Roman mission is going to do. So with that, thank you for coming, Scott.
Thanks for the invitation. Yeah, I was down in LA for a couple months, and I thought I would be remiss if I didn't come up and visit. I haven't been to LCO in a while, so thanks for the invitation. As we were talking about earlier, I gave this talk yesterday, a version of this talk very close to this version to this talk yesterday at UCSB. So if you were there, you are excused. This is you're not going to hear anything new. But for those of you that weren't, I'm hopefully going to tell you a little bit about doing exoplanet demographics with the Roman Space Telescope. So this is a relatively small audience, so I'm happy to field questions during the talk if you'd like. I probably have more material than time to cover it. So you know, there's don't worry if you feel like you're slowing me down. I'm going to have to eject some of the material anyway. Let's see if I can move forward. Okay, so I like to motivate exoplanet demographics talks by thinking about planet formation. I think this is one of the main reasons why we study exoplanets, is to understand how planets form. You know, maybe so that we can understand our own origins and our own solar system. But if you believe in a bottom-up planets formation scenario, is there a place I should stand so people can see me?
No one can see you.
No one can see me. Okay, good. I'm a faceless voice from above. If you believe in a bottom-up planet formation scenario, then if you think about it, you have to understand the physical processes by which micron-sized dust grains, which condense out of protoplanetary disks, grow by sort of 13 or 14 orders of magnitude in size and 38 and 41 orders of magnitude in mass to become the mature planets that we see today. And as you traverse those many orders of magnitude in size and mass, the physics that governs the agglomeration of particles, the building of planets, changes dramatically. And that's actually that's the main sort of difficulty with understanding planet formation, is capturing all of that physics over such a large dynamic range. So that is proven to be quite hard. So you know, but before 1995, you know, this was the one planetary system we knew around a normal star. And you know, if you and I've done a little revisionist history and removed Pluto, but if you you know, if you think about the architecture of our solar system, is very interesting, right? You have four big glorified balls of rock, that you know, oxygen, magnesium, silicon, and some iron, sitting very close to our home star. And then you have the biggest planet, which is mostly hydrogen and helium, sitting right in the middle. And then as you go further away, the planets more or less decrease in mass and size and increase in heavy element content relative to Jupiter. So that architecture is very interesting, and given, you know, a few hundred years to think about it, we came up with a pretty good story for why our solar system looks the way it does. And I'm just going to give a very qualitative, you know, back of the envelope kind of just overview of the story, not doing this justice, and I'm not a planet formation theorist, so you know, forgive me if I kind of gloss over some of the pertinent details. But the basic idea is that planets are sort of the leftover dregs of star formation, or as my colleague at Ohio State University, Chris Kachenik, likes to say, they are the round-off error of star formation. And so stars form in molecular clouds. Some part of that molecular cloud becomes unstable under gravity. It starts to collapse. As it collapses, it conserves angular momentum and forms a protostar in the center, but then a hot accretion disk on the outside. That accretion disk starts to cool off over time. And as it cools off, materials begin to condense out. And the temperature in the midplane of this disk is hottest closer to the protostar and the coolest as you go further out. So the kinds of materials that can condense out of the protoplanetary disk change as you go from the inside to the outside part of the disk. So very close to the star, it's too hot to have any solids at all. Eventually, it becomes cool enough that you can have iron and nickel. Go further out, you can start having rock, silicon, magnesium, and oxygen. And then you reach a magical point in the midplane of the disk as you go out where it becomes cold enough to have solid water ice. And since the two most abundant elements in the universe that like to combine with other elements are hydrogen and oxygen, the solid surface density in the protoplanetary disk jumps by a factor of several as you traverse beyond the snow line. And that means that the planet formation timescale just beyond the snow line is shorter. You have more material and the dynamical times are shorter. So you can rapidly grow to a mass of about 10 Earth masses. And then at that point, you can start accreting hydrogen and helium. And you can all do this all in less than 10 million years, which is the typical timescale for dispersal of a protoplanetary disk. Interior to the snow line, you have less mass. And so you form smaller planets. They never reach this critical mass to accrete a large hydrogen and helium envelope. And their timescale for formation takes longer, maybe 100 million years. And so that basically, and as you go beyond the orbit of Jupiter, the planet formation timescale and the efficiency goes down. So you form smaller planets and you accrete less hydrogen and helium because the planet formation takes longer. That's the basic model for why our solar system looks the way it does. And, it matches the data very well, not surprisingly. So we all know what happened next, though, in 1995. A planetary companion was discovered around 51 Peg by Michel Mayor and Didier Queloz. This is a planet that has a mass of roughly 0.6 that of Jupiter. So it's almost certainly hydrogen and helium dominated. And it's located only a few stellar radii from its parent star. So well interior to the place where our terrestrial planets would live, and well interior to the snow line, where we think, beyond which we think you can only form giant planets because you have enough raw material and the dynamical times are shorter. And so that argues that there's almost certainly large-scale migration that happens in at least a subset of planetary systems. So that was our first clue that our planet formation theory that we developed to explain our solar system was at least incomplete. And since then, we've discovered lots of planets and we've discovered them a lot around a bunch of different systems. And we've learned that planet formation seems to be very robust. Sort of every rock you turn over, you find a planet. But with that diversity of systems, we've had to think about even more physics that must govern planet formation. So we already mentioned large-scale migration. Since we're thinking about planets around other stars, we have to think about the influence of host star properties, mass, age, and multiplicity, elemental abundances, birth environments. That we can have dynamical interactions with other companions. Half of all stars are in binaries, roughly. So how does that impact planet formation? Tides are important for close-in planets. The disk properties can vary even for a given kind of host star. And of course, there's other models of planet formation, like top-down disk gravitational instability, which would predict very different kinds of planets. So planet formation is really hard. So how are we going to go about trying to understand all the physical mechanisms at work or constrain them? And the way we're going to do this is we're going to use exoplanet demographics. And the hope is that these physical processes at work are imprinted in the final distribution of planet parameters in some way. And so if we can measure the distribution of planet parameters, mass, period, radius, semi-major axis host as a function of, say, host star mass, then we can look for these features and try to use them to constrain the physics that governs planet formation and evolution. So some examples of this is there's early predictions that there should be gaps in the planet distribution between planets with radius of roughly Neptune and Jupiter, because in between there you're accreting gas very rapidly, so it's hard to get stuck in that particular intermediate phase. The large-scale migration predicts that there should be large numbers of free-floating planets. Giant planets should be less common around low-mass stars because those low-mass stars have lower mass disks and the dynamical times are longer, et cetera. And so the hope is that the plan is that we try to measure these distribution functions as accurately possible over a broader range of planet and host star properties as possible, so that we can constrain the physics of planet formation. So that's the goal of exoplanet demographics. We are beholden to the methods that we have to detect planets, and each of these methods is sensitive to not only different physical parameters of the planetary system, but have different biases, some of which can be actually quite severe. And so the methods that we use to discover most of the planets, of course, that we know of today are radial velocity and transits. These are mostly sensitive to large planets with short orbits. We've discovered hundreds of planets or 100 planets with direct imaging. Those are mostly young planets, giant planets at very large separations. We are starting to discover planets en masse with astrometry, although that will have to wait until Gaia DR4 to detect many, many more of them. And then the method that I want to focus on is microlensing, which is very complementary to these other methods. And so by combining all the demographics from all these methods, we can hope to get a complete picture. That combining the demographics from different methods and different surveys is itself a huge challenge, which I don't really have time to talk about. Okay. So every exoplanet demographics talk has to give a version of this slide. This is showing mass as a function of orbital period of the known exoplanets as of a few years ago, and then mass radius is a function of orbital period of these planets as well. They're color coded by the detection method, and you can see all sorts of really interesting features in here, some of which are real and some of which are not. Some of which are telling us about the physics of planet formation, and others of which are just telling us about the biases inherent in the surveys that were used to detect these planets. One thing that's very obvious, though, is that there's this region in the bottom right corner of both of the plots that's mainly devoid of planets. It's so devoid of planets that this is where we choose to put the key for our plot, because there's no planets there to cover up. The other interesting aspect of this is that most of the solar system planets live in this region of parameter space. So we are mostly insensitive to analogs of all the solar system planets except for Jupiter. There's an exception to that, and that's, you can see these little triangles that are cyan triangles. Those are actually planets that were detected by microlensing. So our census of exoplanets is really incomplete in this region of parameter space. So just to put it in kind of stark relief, this is a plan view of our solar system with the orbits to scale. And you can see the giant planet orbits. And then there's the terrestrial planets inside the little circle. That is Kepler's search area. So everything outside of there, Kepler was completely insensitive to. And by and large, all the other methods as well, with some limited exceptions. Okay. The other thing that's important to note is that the planets that we've just detected are all relatively close to the sun. So most of the exoplanet detection methods we have rely on detecting photons from either the host star or the planet. As a result, they tend to be magnitude limited in some form. And so most of the planetary systems we've detected live in a kind of a halo of 100 parsecs or so around the sun, 200 parsecs around the sun. The two exceptions are this kind of plume of planets here. These are planets that were detected by Kepler, which stared in one part of the sky for almost 4 years. And then this plume, which are actually planets discovered by microlensing, which the punchline, of course, is that microlensing is independent of the flux of the lens and the source. And so it can detect planets, lens and the planet, the host and the planet, so it can detect planets that are quite far away. Okay, so why would we want to use the microlensing technique to complete the census of planets? Why would we want to fill in this region of parameter space? And so, you can come up with all great theoretical reasons for this. Like, we still think that planet formation must be most efficient beyond the snow line, may still be where giant planets form, or most of them form. We want to survey a broad mass range in this outer region to understand planet formation. Particularly, we'd like to answer very basic questions like, what lives out there? Is it just singleton giant planets, lonely giant planets, or is it families of giant planets like our own solar system, or is it just a bunch of failed low mass planets that never grew up to be giant gas giants? And then another kind of theoretical motivation is this kind of interesting paradox, which is that the planets that will end up being the planets that are forming in protoplanetary disks, which will end up being in the habitable zone of their parent star, they formed in the part of the protoplanetary disk interior to the snow line. So they formed from material that was almost entirely dry. And so the water, the life-giving water that exists on habitable planets, must have come from outside the snow line, and it must have been delivered by something. So whatever lives out there is responsible for dynamically delivering the water-rich asteroids or comets or whatever to the habitable planets. So in order to understand habitability, we really have to understand what is out there. Okay, so how does microlensing work? Hopefully most people here have at least heard of it, since there's some well-known microlensers in the room. But the basic idea is if you stare at a star long enough, in this case, we're talking about a star in the center of the galaxy, and then eventually another star in the foreground will happen to pass very close to your line of sight to that background star. And very close here is about a milliarc second. When that happens, the foreground star will split the light from that background star into multiple images. Those images are typically separated by a milliarc second as well, so are generally unresolved, although now we have a few cases where we have resolved those images, which is quite exciting. But the background star will also be magnified, and so you get a transient magnification of the background star as the foreground star comes in and out of alignment, and that's a microlensing event. And if that foreground star happens to have a planet, that planet happens to be located near the path of one of these images, then that gravity of that planet will perturb the light from that background star additionally and give you a small bump or dip on your light curve. And that's the signature of planets that we use to explore these cold outer regions of planetary systems with microlensing. So microlensing has a lot of unique or relatively unique advantages. So because those images pass at regions beyond the snow line, that's where we're most sensitive to planets. So we're most sensitive to planets at a few times the snow line separation. We're sensitive to very low mass planets. In principle, the magnitude of the perturbation is independent of the planet mass. It actually just it depends on how well aligned the planet is with the background image. That breaks down when you're magnifying only a small fraction of the source, the angular size of the source, in which case your perturbations get washed out. That sets a limit of maybe 10% of the mass of Mars, maybe even lower, depending on how good your photometry is and your ability to detect planets. So you're able to detect things that are very low mass. You can detect very long period planets. So analogs of our own ice giants will appear as events, planetary perturbations that are well separated from the microlensing event due to their host star. So this is one of the only methods to detect true analogs to our own Uranus and Neptune. We are sensitive to a wide range of host masses. So basically anything that happens to float along our line of sight to a background source, we can look for planets around them. That's brown dwarfs, main sequence stars, white dwarfs, neutron stars, and even black holes if they happen to host planets. We don't know. Early on in the sort of development of the microlensing field, a lot of us went around saying, well, we're mainly searching for planets around M dwarfs, and that was because a lot of other surveys were focusing on higher mass stars, and we thought this was an interesting advantage of the microlensing method. Well, we kind of overstated the case to this point that a lot of people in exoplanets now think that microlensing is only sensitive to planets around low mass stars. That's not true. We are sensitive to FGK stars. And like I said, brown dwarf hosts, white dwarf hosts, remnant hosts, etc. It is true that the majority of our hosts are going to be M dwarfs, but that's just mainly because the majority of stars are M dwarfs. The typical mass is maybe about half a solar mass if planet formation is independent of host star mass. We are sensitive to free-floating planets because they can act like independent microlenses. We're sensitive to giant moons of planets. Is there an issue?
You're good.
Okay. We can detect multi-planet systems that can create multiple perturbations on the same event. Analogs of our own solar system, including analogs of our giant planets. Wide circumbinary planets, microlensing is sensitive to outer habitable zone planets, and then planets located throughout the galaxy. So we've got planets around stars or compact objects between here and the center of our galaxy, or maybe even beyond. And that means that we can probe planet populations in every major component of the Milky Way, thin disk, thick disk, and bulge populations, and we can do statistical inferences about the frequency of planets as a function of, say, iron and alpha to iron ratios. Okay, so I'm going to say a little bit about what we've learned from ground-based microlensing so far, just to kind of set the stage and let you know where we're going to be with Roman, what we're going to learn that's new. So this is a paper that recently came out from the led by the KMTNet collaboration. Full disclosure, I was not part of this work. But it's very exciting. The first goal of this paper was to present this discovery of a very low mass planet with microlensing. So you can see the main microlensing events there. There's a little bit of a bump there. This is the blow up of that bump. It's not best photometry ever, but you can see very clearly this bump. And if you do a fit to this light curve and then do some Bayesian inference, you find that this is likely, at a period of 20 or 30 years, and a mass of maybe the mass of the Earth, sitting right there in the middle of nowhere all by itself. So that's very exciting. And the detection probability for this event is very, very low. So that means that these might be actually quite common. So the outer regions of planetary systems may have a lot of these cold Earth mass planets, which is exciting. They go on to do their completeness analysis, and then from that infer the frequency of planets as a function of the mass ratio between the planet and the host star, which is the easiest thing to get out of a microlensing event. And that's plotted here. So this is the raw detections, and then the completeness corrected detections are shown in the dark blue. And they fit a power law to this, and it rises to lower masses, kind of like every mass function that we've ever seen does. But they also note that there's some deviations from that they say are significant. So in particular, there's a paucity of planets here at the sort of Saturn mass objects, maybe a paucity here at higher mass objects. And so they fit a double Gaussian to that and say that actually provides a better fit. And that's interesting. Maybe this is telling us about these are planets that formed from solid material, and these are planets that managed to get massive enough to create a massive hydrogen helium envelope. Maybe, who knows? We'll find out. We'll with better data, we could do better on that. But I should note that in this double power law fit, you see this fall off to lower masses, but that's purely a product of the model that they fit. So we don't really know if the mass function turns over at lower masses or not from microlensing. This is actually in somewhat tension with a previous result that came out a few years ago that argued there was a peak of the mass function at Neptune mass. KMTNet doesn't see that. So we don't know if it continues down below that. And so, this is very interesting and exciting work, but I think it really highlights the need for kind of a uniform survey that Roman will provide. The other thing that has been very exciting with ground-based microlensing is the detection of a handful of these events, these kinds of events. So these are very short timescale microlensing events. You can see the star did nothing for decades and then just burped for less than a day. That you can see that here. And this is a microlensing event, and the timescale is very short, and a few hours or something like that. And you can infer that this is likely due to kind of an Earth mass, terrestrial mass, to free-floating planet, or it could be a very widely separated planet where we don't see evidence from the host star. Follow-up observations could resolve that in principle, But if you take the ensemble of these kinds of short timescale detections and infer something about the mass function of free-floating planets with that, this is model dependent, I'll emphasize, but still an interesting result. You find that this is the mass function of that you get from regular microlensing events that matches what we know from just star counts, for example. There's a dip in the mass function here in red, and then the mass function of free-floating planets or very widely bound planets seems to rise as dn d log m to the -1. So that's very steep. And if you compare that to the bound planet mass function from that Suzuki result, not the one I just showed you, you find that the number of free-floating planets likely outnumbers the number of bound planets by a significant factor. And that's super interesting because likely these free-floating planets, if they are indeed free-floating, came from protoplanetary disks. So now you have a mass budget issue where you have to have the mass from the free-floating planets plus the mass of the bound planets has to, of course, be less than the mass of the protoplanetary disks that we detect. And there is some evidence of tension there, which is currently being explored. So I think that, it's important to recognize there's large uncertainties here, and this is an extrapolation below sort of one Earth mass. So we don't know what happens there, but if it continues down there, we will detect hundreds of free-floating planets, and that's very exciting. So I think this might be one of the most interesting things to come out of Roman. If I had to guess right now, I think the most interesting thing that come out of Roman is almost certainly something we haven't anticipated yet. So, okay, so this is great, but ground-based surveys are only going to get us so far. So how do we do better? How do we get this complete statistical census of exoplanets that we want? So many years ago, I wrote down, sort of in the early 2000s, I wrote down thinking about the future of microlensing because I was, starting to apply for faculty positions, and of course they always ask you, what are you going to be doing in 20 years? I wrote down this question, what are the requirements to detect and measure the masses of 100 Earth mass planets with microlensing? And I wrote down these requirements at the time. And the microlensing is great for all the reasons I said, but it also has some downfalls and some drawbacks. And one of them is that microlensing events are extremely rare. So I said if you stare at a star long enough, you'll find a microlensing event long enough. Here is about 500,000 years. So you can't. That's pretty impractical. So instead of looking for one star for 500,000 years, you look at tens of millions or hundreds of million stars to find thousands of microlensing events. Well, monitoring 100 million stars continuously over the time scale that you need to detect planets is challenging. You need a very crowded field of view and a very crowded field and a large field of view. And you need relatively good precision, but not great precision. And so, the microlensing event rate, as I said, is a few times 10 to the -5 per year per star. The detection probability for an Earth, if it exists around a star, is about 1%. And then you have to monitor on timescales of less than 30 minutes to make sure you catch all the planetary perturbations, which you can't predict in advance. So now you basically have said that you have to monitor hundreds of millions of bold stars continuously on a timescale of 10 minutes for a year. In order to do that, you need good photometry, but not great photometry. These deviations tend to be large, so a few percent photometry is great for most things. Better is, of course, better, but isn't necessarily required. You need to resolve main sequence source stars because that's the only way you're going to get enough stars to monitor this hundreds of millions of stars. But also those source stars are smaller that allow you to detect smaller planets. And you want to be able to resolve out unrelated stars so that you can measure light from the lens itself, which allows you to estimate its mass in some circumstances. And then finally, you want to be able to measure the proper motion of the lens and the source as they separate from each other. And that means you need a long time baselines. The typical proper motions we're talking about here are 5 to 10 milliarc seconds per year. Okay, so I wrote all this down back in the early 2000s, and I kind of laughed like this is never going to happen. But the amazing thing is we are on the cusp of making this happen. It requires you to go to space, however. So you need to go to space because you need to get this high event rate, which means you want to go to more crowded fields that tend to be more extincted. So you have to go to the infrared. The infrared also gives you the benefit that the sources that you want to monitor, the lower mass stars, produce more light in the near infrared. It allows you to get the resolution so that you can isolate lens from the light from the lens star and actually resolve the main sequence sources that you are interested in. So I just show that here why resolution is important. This is a simulated image from Matthew Penny of a field towards the galactic bulge from Roman and then from ground. This is a blow up of those fields, and you can see this nice, beautiful source that you see right there. Like, oh, that's great. That's a star that we're monitoring, and hopefully it does, has a microlensing event. But if you look in the space-based image, that star is actually an asterism of 4 or 5 stars. And those aren't even the stars that you really want to monitor. It's these stars that live sort of right there or there or there that are effectively invisible in the ground-based image. So you really have to go to space to do this. Space affords you to complete visibility because you don't have to worry about the pesky sun or weather. Which, here you've kind of gotten around that by building this global network, but that's not always possible. You need you hope to get smaller systematics so you can get better characterization and robust quantification of your sensitivities. And all of this enables science that you just can't do from the ground, or sub-Earth mass planets, outer habitable zone planets, free-floating Earth mass planets, and mass measurements. Okay, so putting this all together, the requirements to do this, to complete this exoplanet census is listed here, and that requirement is, of course, Roman. Not surprise, right? That's by design to some extent. Okay, Roman is not the Roman Empire. Roman is Nancy Grace Roman, who is pictured here. Nancy Grace Roman is the first chief astronomer at NASA, often also called the mother of Hubble because she was instrumental in making Hubble happen. She is definitely an icon and a hero in the NASA astrophysics community, and so we're very happy to have this telescope named after her. Okay, all right, so I have a question here. This is a choose your adventure part. Is anyone interested in hearing the history of where Roman came from, or would you rather hear more about what Roman can do? Because I only have time to do one or the other.
We'll see what can do.
Okay, all right. If you're interested, I can tell you about where it came from. There's good stories there, but all right. So this is the properties of Roman as they were settled upon. The effective aperture is a little bit less than that of Hubble, 2.28 meters. The field of view is huge, 0.281 square degrees, which is laughable, right? Considering, LSST and DCAM and everything. But for space, that's actually a very large field of view. The wavelength is optical to near infrared. The pixel size is about 0.11 arc seconds, so it is undersampled. Important to keep that in mind. It has a 5-year mission lifetime, extensible to another 5 years at least, hopefully even more. And the orbit is at L2. There are 2 instruments. One is the coronagraph, which is designed to be a technology demonstrator to do high contrast active coronography in space, which would be important to prove the technology for the Habitable World Observatory. I could give a talk about that, although I'm not really the one to give a talk about that because it's not my expertise, but I don't have time anyway. I will be focusing on the wide field instrument, which is what we care about for the microlensing. This has, again, this huge field of view is given to us by 18 H4RG detectors. It's a 300 megapixel camera. It's quite impressive. And it's going to do a lot of things. It has 3 core community surveys. 2 that are focused on dark energy and dark matter and its evolution over time. There's the Galactic Bulge Time Domain Survey, which I'll talk more about. There's a Galactic Plane Survey, which has been added relatively recently. Super exciting. Ask Rachel about that. And then at least 25% of the time is going to be devoted to general astrophysics. The calls for that are coming out this fall, or starting. The first call is coming out this fall. So if there's things you think you could do with this instrumentation, with the survey, you should be thinking about it now and doing the simulations you need to show the science that you can do, because this is a huge opportunity, and there's only going to be so many opportunities to propose for these general astrophysics surveys. And there's not going to be a lot of them. There's going to be maybe of order 30 of them, because Roman is designed to be a survey instrument, not a you go and look at something for 2 days or 1 hour or whatever. So these are the filters at your disposal. There's 7 standard filters. There's a wide 1 to 2 micron filter, which will be used for the Galactic Bulge Time Domain Survey. And then there's 2 low resolution dispersing elements that are mainly used to do photometric redshifts and and supernova classifications. This is the field of view on the left. Again, 18 H4RG detectors. in this kind of smiley face or frowny face, depending on which orientation you're looking at. And this is the compared to the largest fields of view on HST and JWST. So it's 100 times the field of view of Hubble and JWST. But importantly, it's actually a very efficient telescope, much more efficient than HST and JWST. So it actually has 1,000 times the sky mapping speed. So it is able to tile large areas of the sky on a relatively short time scale, or, which is what we care about here, smaller areas of the sky on a very high cadence. And that enables a whole range of science. Just to give you a sense of what we're dealing with here in terms of the number of stars and the amount of data, this is a simulated image from Matthew Penny of one of the fields towards the galactic center that Roman will look at. You can see millions of stars in this image that are ranging from foreground main sequence stars to AGB stars in the bulge to turnoff stars to M dwarfs are all shown here. It's amazing. And this is 0.1% of the survey area. So there will be hundreds of millions of stars that we'll be looking at. You know, imagine 1,000 of these papering this room. That's what we're going to be dealing with. Okay, and this is just a blow up to show that. The thing I want to focus on here is if you look here, you know, you can see it's kind of stars all the way down. This is a very full, very crowded field. Okay, so how do we estimate the yield? Well, we come up with a galactic model. Choose your favorite one, Galaxia, Best ensemble, whatever you want to choose. We've actually developed our own in-house custom-made galactic population synthesis model. And so you populate, you know, a field of view, given to pointing with a catalog of stars with properties and fluxes and et cetera. And then you come up with a survey strategy, you know, that you avoid the regions of very high extinction, but you want to get as close to the plane as possible because your event rate goes up. You pick some number of fields that optimizes your yield, and then you cycle through those fields at a given cadence. You simulate images with stars according to this catalog from your galactic model, and then you inject microlensing events in those, and then you inject planets in those microlensing events, and then you see if you recover them. And this is a clear detection of a planet. So this is software that was developed by Matthew Penny, starting in his thesis and continuing through a Sagan Fellowship at Ohio State and now an assistant professor at LSU, and then taken up also by Sanson Johnson, who was a postdoc at Ohio State. And so this was used to kind of come up with a sort of a notional survey for the galactic bulge time domain survey. The actual survey is going to look different from this. If I have time, I will talk about what it looks like. But the notional survey was 7 fields with a total of 2 square degrees in this wide filter with 50-minute cadence, 50-second exposures, observations in other filters to get colors every sort of 6 hours. And the bulge is visible from Roman for 72 days at a time. So we thought we picked 6 72 days seasons, 3 at the beginning of the 5-year mission, 3 at the end. That's a total of 41,000 exposures and 432 days of total observations spread over this 5-year mission duration. And, these are the kinds of planets we detect in our simulations. The left is what I already showed you in case you weren't paying attention. This is a planet at a semi-major axis of 5.2 AU with a mass of twice the mass of the moon. And you can see this perturbation is huge, very high significance, 27 sigma. These are not subtle features, and there's basically no astrophysical pulse positives that we know of. There's a little asterisk on that. You can ask me about it during the questions if you want. The right is a free-floating Mars mass detection, again, 23 sigma. Yeah.
Ms. Right here, earlier in your talk, you had a free-floating planet. I think the author's name was Rhodes.
Yeah.
And that was a ground-based serendipitous detection.
Yeah.
I recall, but was that comparable? I just don't recall.
The magnet. This is a shorter timescale event, a little bit, and a little bit lower amplitude, but you know it's similar. Yeah. But these are rare. So the part of the issue here is these are rarer for Mars, and so part of the issue, the game you're playing, is that you don't have enough small sources from the ground to monitor to see those. Yeah. Yeah. Okay, so Pick your favorite model of the number of planets as a function of mass and their semi-major axis distribution. Fold that through, turn the crank in your simulations. These are the yields you find. The yields are large. They're not Kepler large, but they're large, 1500 maybe, large enough to do great statistics on this. But, you know, don't believe these numbers. If we knew the answer, we wouldn't have to do the survey. Particularly in the low mass end, because of the reasons I mentioned before, we really don't know very well what the low mass end of the mass function is doing. If you put this together and compare what you could do with Kepler and what you can do with Roman, you end up with this plot, which I still find striking every time I put it up. This is planet mass and Earth masses on the left, semi-major axis on the y-axis, semi-major axis. This is Kepler's candidates. This is roughly the region of Kepler sensitivity, or what it would have been if it operated for the full lifetime. And then this is the region of sensitivity of Roman, and then the blue dots are simulated Roman detections for bound and free-floating planets. And then, of course, the symbols are solar system objects. Roman will be sensitive to analogs of all the solar systems planets except for Mercury, as well as giant moon mass planets, either bound or not bound to other planets. And then by combining Roman and Kepler, we'll get a complete statistical census with from 0 to infinity, semi-major axis from 0 to infinity for all planets with mass or radii greater than 1. So this is going to be the statistical census that we really want to test our theories of planet formation. And just to show this on that same plot I showed before, that's the region of sensitivity of Roman. So very complementary. Okay. In terms of, I mentioned that I think free-floating planets might be the most exciting result. The number of free-floating planets you get obviously depends on what you put in, but it's large. Comparing it to this, if you assume this power law fit from the ground-based microlensing surveys is correct, dn d log m goes as m to the -1. That means you get an equal mass in free-floating planets per decade in the mass of the planet. So you get 1 Earth mass planet, 10.1 Earth mass planets, 100 10 to the -2 Earth mass planets, and that's what the dashed line is. There's a large uncertainty there. So at the best fit value, we would expect to detect planets all the way down to 10 to the -3 Earth masses. With Roman, that's roughly Pluto. If it's higher than that, we'll detect hundreds of Plutos, +1 sigma and -1 sigma of this fit. Then we'll get things all the way down to Ganymede, free-floating planets. So we should detect tens of hundreds of thousands, maybe, of free-floating planets, and that'll really provide a crucial input on planet formation by just saying how much mass was ejected from planetary systems. We are sensitive to potentially habitable planets in the outer regions of the habitable zone. So this shows candidates from Kepler as a function of the stellar effective temperature of the host versus the insolation. This is the habitable zone here in green. Gray are Kepler candidates. These are simulated Roman detections, and you can see that the Kepler peters out as you go to the right. Roman peters out as you go to the left. So by combining these two, you could hope to get a better constraint on Ada Earth. Lots of caveats to that, which I don't have time to go into, but we should be able to do a little bit better than what Kepler did. We are sensitive to giant moons orbiting giant planets, particularly wide separation giant planets. So this is a simulation of a Mars mass moon orbiting a Saturn mass planet, 2.69 AU. We don't know of any Mars mass moons in our solar system, but Mother Nature has told us not to be too conservative in our thinking, because there's all sorts of planets we found that we never thought could exist. But we are in principle sensitive to planets, moons, all the way down to the mass of Ganymede. It's just that those are hard to detect, so they'd have to be quite common for us to detect very many of them. But we can probe exomoon demographics. We can detect planets around circumbinary. We can detect wide circumbinary planets. So most of the circumbinary planets we know of were detected just with semi-major axes just outside the region of stability. If they were any closer, then they would be ejected from their system due to the dynamical interaction with the binary. So this shows the subset of the known circumbinary planets. This is the binary semi-major axis. This is the planet semi-major axis, and this cross is where the closest you can get to be stable. So, we're seeing a biased subset of circumbinary planets with transits. That's because we're most sensitive to planets closest to the star. Microlensing is most sensitive to planets near the Einstein ring radius, which tends to be quite a bit further out relative to the binary separation. This is the one circumbinary planet that we know of with microlensing. You can see that we're probing this outer region of circumbinary planets, so we can really combine those to get a better census of circumbinary planets. This is work that's being done by Arjun Molodar at Ohio State. And then this is kind of a wild idea, but if you had a planetary system with multiple planets and it happened to be edge on and your trajectory of your source just crossed right along that axis, then you could in principle see bumps from many of the planets. I'm not going to promise you that Roman's going to see something like this. That would be cool. But maybe you can see 3 planets, maybe even 4 if you have the right orientation. And so you can really start to probe solar system analogs, which is kind of exciting. And Sinclair Jones at Ohio State is working on this as well.
Is there a window that works in? Like obviously edge on, but like how far above or below the plane can you get?
You can't be very far above below the plane. It's kind of the 10. It has to be aligned to within 10 to the minus 3 of the Einstein ring radius or something like that.
Oh wow.
Yeah. That's unlikely, but there are tens of thousands of microlensing events, so maybe there could be 1 or 2 of them. Okay, so I just want to transition now, and I have about 5 minutes. All right, so I want to talk about the statistical power of the Roman Galactic Bulge Time Domain Survey, because even if you don't care about microlensing, even if you don't care about exoplanets, there's a lot to care about with the Galactic Bulge Time Domain Survey and Roman in general, of course. The per epoch photometric precision at a 21st magnitude in this Y filter, AV magnitude, is about 1%. And the astrometric precision per epoch is about 1 milliarc second. You'll get about a billion photons for a 21st magnitude star over the course of the surveys. The number of observations is of order 40,000. So if you can harness the full power of photon statistics and root n down your observations, you can do better than each of these numbers by a factor of 200, which is impressive. Of course, fainter stars, it's worse. Brighter stars, you do better up until you reach some systematic floor, which we don't really know what that is. But there's a lot of data here, a lot of statistics. And you're going to do it for a ton of stars. At 21st magnitude, you get about 40 million stars. 23rd, 100 million. And you're going to get tens of thousands of microlensing events. So you have hundreds of millions of stars with 40,000 epochs of 1% photometry and 1 milliarc second astrometry. What can you do with that? Well, of course you can do a lot, and people have thought somewhat about what you can do with it, but I think there's a lot more thinking to be done. So this is just a laundry list of things that I've heard that you can do with the Roman Galactic Bulge Time Domain Survey. This is incomplete and it's a little old, but just to give you a sense of the kinds of things you can do. And they're all large numbers here, right? Because we're talking about large samples. But the thing I want to focus on for the next few minutes is this one. Roman will detect 100,000 transiting planets. 100,000 transiting planets. And that seems wild, but if you just do the back of the envelope calculation, you can convince yourself that this is true, given all the information I just told you about the number of stars and their photometric precision and the number of epochs. That's crazy. So, people have done very detailed simulations, not just the back of the envelope. The most recent and most impressive is by Robbie Wilson at Goddard, who did a whole full image level simulation, very analogous to what I talked about for the microlensing, injected transits and then recovered them. And here are some recovered transits. This is a 4 Earth radius or Neptune radius planet around an M dwarf. This is a Jupiter radius planet around a solar type star. This is a period of 40 days, which is wild. This is 3 days. So we're sensitive to planets that are actually relatively small, not Kepler small, not even TESS small, but small. And there's a lot of them. So this is showing yield as a function of the distance to the system. And the top is assuming planet occurrence is independent of the metallicity of the host stars. And so it's broken down by radius of the planet, spectral type of the host star, and then galactic population, thin disk, thick disk, and bulge. And what you can see is that these numbers are, large, and you'll be able to detect planets with radii from 2 to 10 Earth radii. So super Earths to Jupiters around up FGKM stars and the thick disk, thin disk, and bulge, all major stellar populations in the galaxy. And there will be lots of them. Only 90 to 95% of these will be, or sorry, only 5 to 10% of them will be smaller than smaller than Neptune, but that's 7 to 12,000 planets. The other thing that's interesting about this is because you're looking at so many systems, you can look for very rare events. So one particularly rare event is these giant planets are undergoing tidal dissipation, or the stars are undergoing tidal dissipation. So the planets should be decaying, and eventually will get swallowed up by their star. We know of 2 examples of this so far from ground-based surveys, but Roman will detect another factor of 5 to 10 more with its survey. And this is work done by a graduate student at Ohio State, Kylie Carden, who just said, I want to figure this out. Let's go write a paper. So she wrote a paper. And this is what we find. So these numbers are uncertain because we don't understand tidal dissipation rates. We don't understand tides really well. But it does show we'll be able to probe not only the rate of planet engulfment, but also the physics of tidal dissipation. So if you combine the transit survey and the microlensing survey just with Roman, then you get this analogous version of the plot I showed you before. It's made by Robbie Wilson, which is showing the sensitivity of the Roman galactic bulge time domain survey as a function of planet mass and semi-major axis, concluding both microlensing and transits. And you can see we're sensitive to all planets with separations from 0 to infinity, because we're also sensitive to free-floating planets with mass and or radius greater than twice that of Earth. And there's regions of the survey that overlap, these 2 surveys that overlap. So you can do interesting consistency checks to make sure the microlensing, which has very different selection effects than the transit survey, are giving you the same answer. If they give you the same answer, maybe you could do some sort of statistical mass radius relationship for planets in that overlap region. I think the possibilities are quite impressive. And you can do this for all major stellar populations in the galaxy. So really, you're getting a complete statistical census of planets in the galaxy. You're going to find all the planets in a statistical sense, except for, this region of inner space here, which is, maybe is important. I don't know.
But put the key.
You need someone to put the key. Exactly. So harnessing the power here that, this is all statistical power, right? Harnessing this is not easy. It is a lot of work. And people are thinking hard about it, but in my opinion, not enough people are thinking hard about it. And I think there's lots of opportunities. Okay. All right. Now what? Roman will launch next year. Okay. October 2026, maybe even earlier by a month or so. We have all of the flight hardware in hand. It's been through environmental testing. It meets all of its requirements. It is on track for an early launch, and there is months of schedule reserve. This is pictures from the Goddard High Bay. There in the corner here is Roman with the little dunce cap on. There's the instrument carrier. The instruments are in the instrument carrier. That's the OTA you can see sort of through there in the back. That's the sun shield popping up. There's a completed OTA barrel assembly with looking down to the primary mirror. So it is basically done, and it will be completed. All the final pieces will be put together after another round of testing in summer of next year, and it will be shipped to Cape Canaveral in the summer of next year, which is crazy. So I am the PI, as Rachel mentioned, of the project infrastructure team for the Argus, the Roman Galactic Exoplanet Survey. We currently have about 100 members. We have 13 working groups, at least one of which is co-led by Rachel, maybe 2, I don't remember. And Katerina has here been helping enormously with this. So we have a public website, and very importantly, we are very close to having a logo and swag. Very excited. So this is the second face-to-face meeting we had at Goddard. There might be a familiar face there. I think Rachel was unable to attend, unfortunately.
Jill's
She's right.
Oh, were you? Okay, I couldn't remember.
next to you, actually.
Oh yeah, okay. Well, just to show. Anyway, so it's very exciting. And our goals are basically to enable this science, to make sure that this science happens. But you know, there's other things we want to do. Is we want to support the overall Roman ecosystem. So there's other projects, infrastructure teams, there's wide field survey teams, science centers, Roman project that all operate together to make this survey a success, and we try to support that. And we want to build a large, vibrant, diverse community of scientists to engage with the Argus survey and mission. And we really want to engage the public. And so there's all sorts of interesting citizen science projects that we could do with this that we're excited to get into, as well as all this great science. They recently finalized the survey strategy. The Roman Galactic Bulge Time Domain Survey got what was called the overguide, which was sort of more than we had hoped for. So we're excited about that. It changes the properties of the survey slightly. In particular, there's only going to be 5 fields instead of 7, but the cadence is going to be shorter, 12 minutes instead of 15. The yields will be similar to what I showed, and we're still working through the implications of this, but they're not going to be very dramatically different than what I just showed you. I just want to mention that we have been thinking hard about contemporaneous and precursor observations. We're successful, we being Amon Karens and a bunch of other people, not really me, we're successful in getting Euclid to look at the fields of the galactic center and get some precursor imaging, which is fantastic. We're very grateful for that. Sean Terry had a 180 pointing HST orbit, HST's proposal to do precursor imaging of about 40% of the fields in a couple of filters, 4 filters. That's exciting. And so we can enable all sorts of science, including we can look at historical microlensing events and look for detections of the lens flux, which you can see in this particular event. And that allows us to, and there's thousands of these, that allows us to infer the mass of the lens or with some additional data. I just want to spend this last minute on this slide because I'm here and I think it's important to think about contemporaneous observation. This is something I will admit we have not thought as much as we should have as a project, although there are people like Rachel that are thinking very hard about this. But there's a whole host of microlensing surveys that have been ongoing and hopefully will also image this field as the Roman survey is happening. LSST has great, enormous potential, and we'll be monitoring the fields both during the seasons and then outside of the seasons as well. So this is from a presentation Rachel gave during, I guess, our most recent meeting, showing how LSST can help fill in the gaps between the Roman seasons. And I think it's worth thinking about not only what these microlensing survey telescopes can do, MOA, OGLE, KMT, but also ground and space-based telescopes with smaller fields of view like Las Cumbres. I think the science that is enabled from this includes getting higher cadence. 12 minutes is great, but higher cadence is better, particularly for high magnification events where the time scale for the deviations can be shortened. A lot of the high magnification events will be saturated in Roman data, so we can alert on those. We can follow them up and get complete coverage. Those happen to be nearly 100% sensitive to planets if they exist. Multi-planet systems are especially sensitive to those. I think there's interesting science there. Of course, improved characterization. I think there's a lot to be thought about here. And the important thing to mention is that a lot of this science, at least especially with the small field of view, obviously requires alerts. And alerts are not going to happen with Roman naturally. So how are alerts going to happen? So we were having conversations earlier today about this. The more I think about these kinds of things, the more I think we need to have kind of a summit or a meeting of people that are interested in participating in this science, that have access to ground-based observatories or even space-based observatories, to get together in a room for a couple days and just think about what could we do and what is the best way to coordinate this. So I appreciate this visit because it really kind of forced me to think about this, and I think there's a lot of potential there that could be realized. And so with that, I will say thank you. You can read this if you want, but let me know if you'd like to be involved, or let Rachel and Katarzyna let you know if you want to be involved. Thanks.
Thank you very much, Scott.
Yes.
Start with a question.
What does it mean that alerts are not going to happen naturally?
So the most useful kind of alerts would be alerts that happen on a timescale of essentially instantaneously after the images are taken so that we can get planetary perturbations, covered planetary perturbations. So if you can alert on a planetary perturbation, then you can cover it and get very rapid turnaround, then you could cover it. That would be great. Roman said that we initially, when we were developing Roman, we asked if we could get alerts right away, and it was too resource intensive, and they just said no. So we will be able to alert on data that's sort of taken a few days after the initial images, but it's not going to be taken now. It's not going to be alerted by the project. That said, there is a project infrastructure team called Rapid, whose main goal is to alert immediately on all difference images that are taken. They're going to take difference images of every epoch, of every field that Roman points to, and alert on those. So I think that's the framework that we can start working with.
So what is the cadence for that then? I guess, I mean, rather than
So they are hoping to issue alerts.
about
Yeah, so
the event itself.
my understanding is that the images will be downloaded and processed to level 2 within do you remember this number, Rachel?
No, off the top of my head.
A few hours or something like that. But they're not promising immediately available. I'm not sure. I actually don't know the answer to that question.
So, but the start of the microlensing event itself, though, could be distributed.
Right. So we could alert we could alert on the longer time scale primary event, and
Okay.
there's no infrastructure in the formal pipeline to do that. But one of the things we as a pitch should do is either do that ourselves, or make sure that other people are doing that. Yeah.
I can kind of speak to that.
Yeah, I'm sure you thought about this more than I am.
The Rapid team, if they can provide us alerts and data, they are pretty well plugged into the general alert ecosystem of software of which we are very familiar. So they will disseminate those alerts through things like the alert broker systems. Our software's already plugged into that. So provided they can send us that alert stream, we can continue what we've been doing for many years, following up the brighter events. Obviously, the issue for us with Roman and Rubin is that a lot of the target stars are way too faint for us, but they will follow those up themselves. For the brighter targets, those we can prioritize, and we can get the higher cadence follow up for those.
Yeah. My question was more wondering how rapidly your Tom is going to be fed, basically, from Roman.
Skylar Van Dyke, right?
Yeah.
Yeah.
I'm trying to get him to come here and talk about Rapid.
Yeah.
So hopefully
we'll have a follow-up.
we will you can like ask questions.
Can badger him directly.
Yeah.
So we are actively just engaging with the Rapid collaboration. Yeah.
I have a question. So first of all, unless you want to ask?
No, go ahead,
Okay.
please.
First of all, what was the possible contaminant for the little term short?
Oh, right. So I don't know if you've been following the saga, but there's there's a team led by Michelle Kunimoto, including Will DeRocco and Neil Nolan Smith and Steve Howell, that did a search for free floating microlensing events in TESS. They came up with this one candidate, which looks for all the world like a free floating Earth mass planet. But the probability of seeing that in the one sector that they looked at, or the two sectors they looked at, is small, like 10 to the minus 2, 10 to the minus 1.
Okay. Yeah.
Yeah. So, so maybe that's a new kind of false positive, a flare. And the star also happens to be variable and rotationally variable. So maybe this happens to be a flare, a new kind of flare, because it's very symmetric, and flares are not generally symmetric. So it's a very symmetric flare. And the other thing about the flare is that the total energy output of this flare is 2 orders of magnitude larger than any other flare that was detected in the TESS data.
Wow.
So it is a weird ass flare if it is a flare. It is also a surprising microlensing event if it's a microlensing event. So if these kinds of flares are as common as you might estimate based on, if it is a flare and they are as common as you'd estimate based on this one detection, they are going to outnumber the number of free floating planets by a factor of several. You can ask the question, why haven't we seen them already? I don't know. I don't think anyone's done that calculation, but anyway.
Could be.
Is they any
Yes.
form of asteroid?
They did all the moving object checks. They did it really. They sent it to me because their first referee was very negative about the paper. So they sent it to me, and I gave them a whole list of comments. It ends up making me co-author, but I am convinced by all the analysis that they did that it's not some obvious false positive. It must be something new, either a surprisingly rare microlensing event or some weird flare.
Question. So I know for a lot of microlensing, the lens is not necessarily visible in any way or whatever with the telescope you're using to do the microlensing.
Yeah.
Sounds like with Roman, you're gonna see a lot of the lenses.
Yeah. Uh-huh.
Is there any, does that, I mean, presumably that's helpful when the lens isn't lensing. Is that a problem when you're actually like having the lens effect and
Oh, there's some dilution of the signal because the lens is bright, but the lens is typically not much brighter than the source. It's typically fainter than the source, and if it is brighter than the source, it's not much brighter. There's a few cases where it has been much brighter, but yeah, it's not a huge effect on the detection sensitivity. And it's all folded into the simulations we do anyway, naturally. So I'm not worried about that. But yeah, Roman will be able to detect the lens in many cases. The very things at the host stars that are at the bottom of the main sequence and brown dwarfs might be tough. And of course, if they're actual remnants, we won't be able to detect the light from the lens. And if we can measure the mass independently and then show that it's a 1.4 solar masses and then not detect the light, then it's got to be a white dwarf. And there's already been 2 white dwarf hosts of planets detected by microlensing that way.
but that would presumably also give you a way to know, or at least have a better idea if a free floating planet is actually free floating or just really
Right over. Yeah, there is analysis from Radek Polecki from University of Warsaw where he analyzes like these wide orbit microlensing events. Sorry, yes.
Yeah, so you
Like
yeah, so you can use detection of the flux from the host star lens to eliminate some of these, and people are actively actively following up the few that we've detected with HST and KEK-AO to try to detect light. I don't know what the results of those are. You can do it with a lot of them with Roman. Again, you're still going to have this problem that if it's bound to a low mass star, but I think just to think far in the future, this is where ELT is going to kick ass. Because they're just going to spend like 5 seconds looking at this and detect everything all the way down to below the main sequence and, probably all the way down to the bottom of the brown dwarf sequence. So I think that's a very exciting prospect. Yeah.
So I'm interested in the time series astrometry that Roman will produce. And I think after the duration of the multi-year duration of the Galactic Bulge Survey, we should have really good astrometry time series for everything in the field. Now, I know with Gaia, when they did that, they were actually predict microlensing happening in the future. So what scope is there for, you do the Argus survey, you predict microlensing events in the future, and then use an astrophysics proposal for Roman to go to follow them up in the extended mission?
Well, I mean, Roman's field of view is large enough that you wouldn't, you'd probably just do the same survey again to detect those, right? The question is, could you use narrowing? So if you could predict when the microlensing events are going to happen, you could then use AO from the ground to follow them up, right? The only reason you can't do this from the ground is just that you can't do AO over 0.3 square degree fields of view, right? If you had multi-conjugate AO and it worked really well over those fields of view, you could just do this from the ground. But so yeah, you could predict these things and then go pick them off one by one with, KEK-AO or ELT-AO and do that. That's an interesting idea. I hadn't thought about that, but you should be able to do that. Yeah. It's exciting.
Can I? Yeah. I have a question about Roman extended mission. So there is possibility for extra 5 years. What's like the limiting thing that could cut beyond the total 10 years that would that,
What limits the lifetime ultimately?
yes, yes.
So assuming there's no failures, it is propellant.
Oh, yeah, okay, so it's the Gaia, the
Yeah,
old
yeah.
Gaia thing, okay.
Propellant. But you know that I've been told that that should last more than 10 years easily.
Okay.
There's degradation of the solar panels also matters. So this is important for the bulge because the angle at which you can have the incident angle of the sun on the solar panels is going to get narrower and narrower so that you get enough power to keep the observatory running. And so your bulge seasons are going to get shorter and shorter as time goes by. That'll be another thing, but you know, I think that's relatively slow.
Yeah, but it would also be a possibility to like focus on extra, disk regions or like Magellanic clouds, and the.
Sure. Yeah.
Okay.
So, I mean, I think thinking about what's, you know, it's a little crazy to think about what you're going to do in the extended mission right now, but I do think it's important because you want to think about what it is you need to get out of the survey early so that you can plan for the extended mission proposals, right? You know, if you just wait until the 5 years is over,
Yep.
figure out what you've learned and said, okay, well, this is what we really want to look at, then, you know, you've wasted a significant amount of extended mission time. So, you know, I think it's important that we think about what data products we want to get out early that will tell us, inform our strategies for future things. So, you know, for follow-up proposals and extended mission. So, you know, it might be that we just choose to look at one field at you know, 1 minute cadence. But it could be that we find that there's just not a lot of small things out there, and maybe that doesn't make sense. Anyway, we don't know.
It's also worth like thinking about what can be done to expand the results of the nominal mission, because for example in Gaia they figure out, oh, in extended mission we can like rotate Gaia backwards, and this will help to break some degeneracies in astrometric solutions. So
Yeah.
there's also something like that people can think about.
Yeah, and I mean, of course, you know, we're going to learn so much in the first year of figuring out what's going on that I think that's going to inform those kinds of things. You know.
Okay, we are super over time.
Oh.
Yeah.
I will maybe stop recording now.
Let us thank Scott
Yeah,
one more time.
Thank you.